Good morning, everyone. And thank you, people who are here in Kobe. Also, thank you for people who are joining online. 9 a.m., a little past 9 a.m. in Japan, but also could be elsewhere in the world. We appreciate your interest and participation in this event. In fact, we have a two-day event which is truly live, although we still have an online element for the first time in 4 years. And also, we will have a series of meetings, both internal and external, throughout the week. And this really is an important week to propel our supercomputing capabilities forward towards the 2030s. Okay, so firstly, a bit about Fugaku. We already know the machine already. We have a tour. It's a very large supercomputer. He has almost 160,000 nodes. He uses 60 megawatts of power. So you think if that's a lot of electricity, probably the machine with highest number of nodes and largest power consumption, at least public. But also, if you divide 60 megawatts by 160,000, that's about 100 watts per node. So it's a super power efficient machine. Don't believe in the green 500 numbers, they're insignificant. What's important is in the production, and Fugaku is a very power efficient machine thanks to all the technologies, both in hardware, software, and in operations. So it's been running for over 3 years. It's been a fantastic success. Not just acknowledged by us, but acknowledged publicly, helping to mitigate COVID, helping to prevent disasters, helping to move the industry forward. And when you think about 160,000 nodes, well, some of the codes, like bandwidth-bound codes, Fugaku's A-square effects can be as powerful as a GPU of the similar time, for example, in NVIDIA V100. So, it's got 160,000 of them. Now, when you put this in context, so recently with the AI craze, it was reported that all the tech giants like Google, Meta in particular, and also Microsoft Azure, and Google's not up to that speed, has acquired a whole bunch of GPUs, and they amount to about 100,000, 130,000. And of course, they'll acquire more this year, apparently. But it leads to the point that the number of processors, chips in this machine equals that of what's there in the cloud, at least at this moment. So, of course, the hyperscalers are growing, but we were there 5 years ago. Right? And if we have more money, of course, we can build more. So this goes to show that we are, despite all the media, social attention to hyperscalers being ginormous, we are also very ginormous. And in fact, it's our technology that they're utilizing to create such machines. So, it's won accolades, it's got the Gordon Bell Award, solves societal problems and such and such. So I'll highlight maybe one thing which is not COVID, since we're recovered from COVID. So this is a Gordon Bell Climate Modeling 2022. It didn't quite win. It almost came close. It became the finalist, and it was a very close call. But it was still nonetheless a finalist for the climate modeling special award. And this was actually work done 2 years ago by a team led by Takemasa Miyoshi and also Hirofumi Tomita. So Tomita had this new code Scale, which was a very high resolution, extremely scalable weather and climate simulation package. And he worked with Miyoshi's team, who has specialty in data simulation. And they did a real-time forecast, more than real-time, of the very high resolution weather forecast to prepare for the Tokyo Olympics, to not mitigate so much a big disaster, but small disasters like sudden rainfall, or you get it gets so hot, you get a heat spill, you want to evacuate to a nearby building which is air conditioned. But how do you tell that? You need high resolution and also extremely accurate real-time prediction. So they went about and they commissioned what's called a phase array radar, which can scan the sky at more than 100 frequencies at the same time. It's the latest radar. It's state-of-the-art radar they have. Not a single frequency, but hundreds of like more than 100 wavelength. And then they get this massive real-time incoming data stream of these scans, which can encompass more than 50 kilometers radius. And then this real-time data was assimilated with the multi-petascale real-time weather simulation on Fugaku, running at about 9%, about 5 million cores. And then so you get 30-minute to you get about a 30-minute ahead of time weather forecast, but you have to repeat this every 30 seconds. So usually weather forecasts are repeated in hours, but it's a 30-second interval thing. And then the results are updated real time in 30-second intervals. And then it was sent over to a commercial service which transmitted a customized weather forecast 30 minutes ahead of time, 30-second update to your smartphone, okay? Which is, of course, location aware. And of course, this was supposed to prevent a lot of not only uncomfort, but some of the dangers like heat spell, which may have been disastrous for something like Yeldry. Unfortunately, Tokyo Olympics was, due to COVID, mitigated that circumstance because because it was held without audience. But still, it worked. So here's the overall scheme. So it would have the radar, would have an outer domain, coarse resolution simulation, then would have an ensemble, 8,000 nodes, with 1,000 ensembles of about 8 node simulations, and would be doing this simulation and data simulation at 30-second intervals. So an exascale class machine can do this kind of societal good. And moreover, then this can be used with the use of digital twin technology to forecast, okay, so this is successful in Tokyo. So can we do this throughout Japan or throughout the world? Can we do 30-second real-time forecast? And if so, how many radars do we need? Where do we place them? So then you can do a what-if type of analysis. And this is work done later by the team, saying, okay, where do you place the radars optimally in Kyushu? So this says you need about 15 or about 20 or so radars. But if you place them strategically, you can do this high-resolution, sub-500-meter, 30-second update forecast in real time, 24/7. Of course, you need a machine like Fugaku, obviously. But this is sort of a thing that now the technology allows you to do. And also, a similar thing was done by the Meteorological Agency, our Weather Bureau. So they, for the first time, they worked with us to implement this high-resolution weather forecast, working with also University of Tokyo, JAMSTEC, and also RIKEN application team, because the torrential rain band is becoming a significant problem globally. You see floods, in Europe. We see with sudden rainfalls. Of course, we get torrential rainfalls in Japan, which is wreaking havoc in areas in unprecedented precipitation. But forecasting these are very hard because it's very chaotic. So if you look at the right-hand side, there's a 5-kilometer resolution forecast that the JMA is doing. This is, it's nowhere compared to what's the left-hand side, which is reality. But now, with the high-resolution forecast capabilities with the new models afforded by Fugaku, they did a lot of research for the first time on an external supercomputer, Fugaku, and they came up with the science and of course the program to be able to accurately predict these torrential rainfalls about 12 hours to 24 hours ahead. So they were so happy with the result, they bought twins of Fugaku. Actually, they bought 2 machines. And when the meteorological agencies buy 2 machines, they know they're serious. Because if just for experiment, they don't need 2. They only need 1. Why did they buy 2? Well, they want to make this immediately into production. And they are going to this year, apparently. So again, this type of... Fugaku, the president's Fugaku, is no longer about doing some demonstrative science, but it's about solving very difficult societal problems, helping the industry. So it cannot be, so the success of Fugaku attributed to building a general purpose machine, which is easy to program and you get high performance. And you get lots of applications, both our own, but also external. So a lot of DOE codes are running on this machine, for example. A lot of public open source domain codes are running. A lot of ISV codes are running on the machine. And we didn't quite successfully make the chip be available in the cloud, unfortunately. And I won't go into the details of that. However, as I will detail later, our partners at Amazon created a compatible chip. And now all these scientific results can be permeated to the cloud as virtual Fugaku. Right? So this is very important. So this kind of generality, ease of programming, getting performance, was tantamount to the success of Fugaku. In fact, we had the Hyperion Research do analysis of the economic impact of Fugaku, which costs more than $1 billion to build. It's costing more to operate. But they estimate, and this is their word, not ours. Hyperion is a very reputable, HPC analysis firm that consults for a lot of European centers, DOE centers, NSF centers, and all around the world. They said that the economic impact of Fugaku is nearly 2 orders of magnitude beyond its cost, up to more than $100 billion US. So the Japanese government's got a great deal. I think people got a great deal. That building this supercomputer and designing and building supercomputer has a significant societal impact and payback. Again, it's not about building the machine. It's not building the fastest. It's not about building the fastest supercomputer in the world. It's not about impact. Right? It's about solving real problems, right? Real societal problems to have impact. And that's why the AI has so much proliferation. That's why Google's and Amazon's, they're investing so much in high-performance computing now, because it's tantamount not only to the business, but they believe it'll change the society as we know it for the better. And that's very important. So where are we going? Okay, so we are, of course, pushing forward with improving or making another order of magnitude leap in performance in terms of conventional computing. But of course, we know it's getting hard. But also, there are new computing paradigms like AI, science, or with quantum. And we always need to think about, but here we always need to think about science of the particular technology, like high-performance computing, high-performance AI, high-performance quantum, and HPC hybrid. But also really need to think about science by these infrastructures. So again, building a exaflop or zetaflop whatever machine is meaningless unless you get the sciences done, unless you advance the science, unless you improve the industry, unless you solve impactfully societal problems. It's meaningless. Okay? So we always have to think about science by high-performance computing, science by high-performance AI, and science by Quantum-HPC hybrid. That's the most, so those are also important. And of course, they mutually affect each other. Okay? Because unless we have a good machine or good software with good algorithms, we cannot do effective science. Unfortunately, so FugakuNEXT feasibility study is ongoing. We'll get to that. We are Science from High-Performance AI. RIKEN now will will be a program which will be launched April 1st. This is all RIKEN program. It's called TRIP AGIS. But of course, there's a bigger Science for AI program within RIKEN, but the TRIP AGIS will be the core program. And this will be funded for about US $500 million. And there is a TRIP hybrid Quantum-HPC project deployment, which will be, which was announced, which is about $140 million, and will be deployed. And this will not be possible without excellent research people we have. We will be upgrading our organization. We're hiring new people to cope with these situations, these new challenges. In particular, we'll be hiring new, we just hired a new PI to work on large-scale digital twin. We're recruiting 2 female PIs, female exclusive. So if you know anybody who would like to apply, it's closed. The initial call closed, but if you know anybody, we'll be very much focused on hiring someone. We'll have a new deputy director, Yuji Sugita, one of the top molecular dynamics researcher, but he'll be taking on the role that was occupied by Ms. Sato. But Masato-san will now focus on the new Quantum-HPC hybrid platform division. So he wanted to focus on that, so he moved on to this. And in spring, we will be announcing the AF for Science platform division. So again, our center is growing. It's like the number of PIs are probably like twice the size. And we'll be going beyond twice the size once we start the FugakuNEXT R&D. So again, our organization is growing very rapidly. Okay, so about the platform. So why do we do this? Well, it's all about the platform. Because so why is Amazon dominating shopping, and how does it change the society? When you think about it, so in the past they had all these little shops that people went around with their shopping carts or cars or pedestrian with shopping bags, and there were no sharing of data. They were individual storefronts. They were maybe sometimes they're like shopping centers or department stores, but still very local, very domestic. But then with the internet, and now with the cloud, everything changed. So Amazon, there are virtual storefronts of different merchants, but underneath it's a cloud infrastructure where all the data is collected, they're analyzed, and then of course every transaction goes through the system. So, and why is Amazon winner? Well, because they dominate the platform. Okay? So they get all the data, they can optimize, they can recommend, they can do all this stuff. So of course, that's making Jeff Bezos made him very rich, but also it's a convenience for us. There are a lot of elderly people who couldn't go shopping now can shop, right? In fact, they can shop around the world because of this platform. Same with science. So even to today, there are little storefronts like labs, right? And how do they share info? Well, there's info by paper. Well, now it's electric paper, but paper, like papers. Right? But this will change in a similar way. There will be digital platforms for domains. And these platforms will collect the data, will collect the simulation, collect AI, will facilitate AI. People will be sharing data dynamically on the platform. They'll be sharing code. They'll be sharing everything. There'll be platforms for pharmaceuticals, smart city, power grid, or whatever, or transportation, whatever. And then who will rule the science? Well, it's the platform. So it's really important to build platforms that can accommodate this vision and be general purpose and very widespread and connect with the other platforms, namely the cloud platforms out there and instruments and everything, such that the platform will be able to accommodate the entire community. Okay, so that's how we advance science. It's a very similar way to how shopping evolved. So it's not about building one machine. It's not about building the next giant exascale machine. That's inconsequential. It's about building the platform. Okay? So building a platform, I'm sorry for some of the Japanese. So we're building, a team led by Professor Dr. Okuno. He's building a very comprehensive pharmaceutical platform, hoping to innovate, shortening the length of time to create these drugs by half. But this platform is basically also a pharmaceutical pipeline workflow, which consists of tens of components. So it's no longer about running just one ginormous run, Limpack run. Right? It's about being able to facilitate lots of components, which are AI components, which are simulation components, which are data components. Different components are strung together in a workflow with the user interface, with the databases, federated learning interface, federated learning capabilities. So to get science done, we need to facilitate these types of platforms that, again, consist of tens to hundreds of these heterogeneous components. It's not about running one gigantic application. Those days are gone. We're also building a platform for smart cities and also being able to simulate things like earthquake and tsunami. Of course, we have the codes, right? But we also need very detailed geographical databases that depict the properties of each buildings, the bridges, the roads, everything. We need to know about the traffic. We need to know about how people are moving. We need how the infrastructure. We need details of every house, every building, in order to be able to do accurate simulation. We need a data platform to accompany the simulation platform or tightly couple these platforms, and we're building that. In fact, with these, I'm sorry, Japanese. In fact, we realize we do have the elements, because when you try to simulate the functions of a smart city. So, for example, Toyota has built this virtual, not a real future city, for real. They call it the woven city. But in retrospect, you don't really need to build that kind of stuff. You can build these digital twin cities. But in order to build digital twin cities, you need all these elements. Right? You need the buildings, you need the data. And you need to replicate all the physical phenomena and societal phenomena that happens in the city. And once you have that, then everybody in the community, people who build, the real estate, the people who design buildings, people who design cities, people who prevent disasters, they can all come to this platform. Because all the elements are there. The building elements are there, the disaster elements are there, the weather elements are there. All the elements are there, and they're coupled together. It's like a gaming platform. And once you're in there, all it takes is a little bit of effort, which may be automatable by AI, to create your own digital twin in your own societal situations to replicate what will happen, and then do a forecast or prediction of what will happen, and then do appropriate planning to mitigate those, or even to profit from those situations. So building a smart city platform is another one of our goals, and that's why we have a new team to do that. But they will be in collaboration with many other teams, both inside and outside, to create these digital twin platforms. In fact, these platforms will transcend a single machine. They should reach the cloud, because at the end of the day, right? Well, I said, well, I have 106,000 nodes, but still, compared to what the hyperscalers will be facilitating, they'll not be large. It's in fact, our machine is already full. So we get more demand. We can't satisfy those unless the government gives us the money, or we can build the next machine. Then, of course, that'll be filled up. So we're teaming up with AWS because they happen to create this new, well, I don't think it happened. I think they were influenced by us. That they have built their own ARM platform. So Graviton, now they just announced Graviton 4, which looks very much like A2FX4. And then what we're trying to do is to create an environment where, in collaboration with platforms, such that all the Fugaku's software will translate transparently onto AWS. So a virtual Fugaku. Yeah. And this has many purposes, but one is to disseminate the results and the platforms we create on Fugaku. Because at the end of the day, a lot of people focus too much on hardware. They say, oh, build hardware. We need new technology development. But they say, okay, what's a new technology development? Well, we have a new CPU. Everybody can build a CPU. That's not the point. The point is the entire ecosystem. And the ecosystem includes software, the system software, the algorithms, the libraries, the applications. And what the money spent on Fugaku, for example, a lot of money was spent on the software. Look at ECP, DOE-ECP. A lot of money was spent on the software. So with Virtual Fugaku, this allows, if we have a holistic software ecosystem, which is, by the way, a lot of people give us quite a bit of accolade for creating a very system that's very easy to use. Every year we have a high school student contest. And the smartest high school students in Japan, they come and use Fugaku to compete. And these are kids, although they're smart, use these supercomputers for the first time. And they said, and we always ask them, have you had problems using Fugaku? I said, oh no, it was really easy to use. It was even better than my home PC. And that's because it's a very rich and easy to use environment. So if you take an environment like that, how can we isolate it to be within Fugaku? We should, that's actually Fugaku has more than 50, and probably moving on to 100 applications pre-installed, just like your pre-installed PC. Or better, even better than your pre-installed PC. You buy it you buy online. So we'll try to create this Fugaku distro. Hopefully this will become more of a community phenomena. We don't mean to dominate this. And this will allow us to extend our platform, both internally and externally. And also, hopefully this can migrate to other supercomputers. Because again, our results are not just limited to hardware. It's only part of the game. Our results are the software, the applications, and the sciences. And to make things easy to use, for example, we've done we've done customizations of open on demand to create this Fugaku on demand. So now this is the default user environment. We no longer recommend people to do SSH, all these arcane stuff. We recommend when they come online, we'll use this environment. Just go to your browser, and you get all the status on your browser. All the applications are pre-installed. Right? And sorry for the Japanese. This is there are more than 50 apps pre-installed. This list is growing, and then we can just you can get a list of installed apps, just like on Windows, and for good Linux distro environment like Ubuntu. You can just launch the apps, easily. Just launch this, and then it works. And then once you get the result, you can visualize the result. This is a desktop running on. By the way, this is a desktop and a browser running on a Fugaku node. So all this is running on a Fugaku compute node, and sent to your, of course, remotely sent to your PC. So, because we allow all the Linux functions on Fugaku nodes. So, and of course, you can access, you can do batch submissions, and of course, but it's a much better interface than arcane textual teletypes, which is more than 100 years old. You can manipulate files just like with the browser. Again, the basis, the open environment is a wonderful environment, and but of course, again, we did a lot of work to customize the environment, and we are going to make this available as part of the virtual Fugaku package, so people can just go and run using a very familiar GUI interface. But again, if you're an old type, you can always use this again, but this can be done from a browser. But no SSH key to import and none of that. This just works immediately. Okay, so that's the ease of use. Okay. Now let's switch gears a bit and talk about the 3 directions that I mentioned. So about AI. So this is AI for science. So this is a slide Rick Stevens kindly gave to me that I added a little bit. So, but his direction, our direction are completely in line. So I take the liberty of using his slide by adding a little bit of element. So how do we use AI? So AI for science is not about, okay, let's put it this way. There are 2 mistaken cases of what AI for science is. One is what I call a little sprinkling of AI. So you have this big science, you have a science, you've done like lab science or whatever. And then instead of using your like R package, you sprinkle a little bit of AI to improve maybe your statistical analysis. You sprinkle a little bit of AI, you call it AI for science. That's not AI for science, right? The other extreme, which is again not AI for science, you have your AI researcher, you have this brand new, fantastic training algorithm. Oh, but it's really not good, useful for most things. Oh, but there's one toy application in science that may be useful for us. That run this toy stuff, and demonstrate. Oh, yeah, my training algorithm is the best, next best thing. Since AlexNet, that's not AI for science. It's a toy app. AI for science. Just like HPC for science. HPC for science is solving problems that are otherwise not solvable without using large-scale computing. And we all know that. We do that. I don't have to tell you. We all do that. Same with AI. AI for science is solving AI problems that are not otherwise solvable or using by AI or combination of AI with HPC. That's the real AI for science, and that's a challenge. But what do we do? Well, we do things like we do large-scale observation. Then we have things like segmentation, recognition. We do these things. Also, but now AI is used for generative methods. And one of the most popular generative methods is, of course, surrogate models. We generate simulation results, etc. That's very now widespread. But of course, the foundational models will allow you to generate other stuff, like directly generate material structures or genomic sequences and such, or even programs, scientific codes, because scientific codes are not as abundant. So you want these AI to be able to generate codes. Or AI can control experiments or optimize. So ultimately, the AI for science, we believe, will automate the PDCA cycle of science. So the AI will plan the experiment, will conduct simulations or laboratory experiments by controlling robots, controlling supercomputers. And then they will collect the result, analyze the result, and plan for the next experiment. That's pretty, very much like what the AI revolution is in other industries. In fact, that may put a lot of scientists out of work. Well, probably not, because what the other industries experience is not, well, there are people losing work, granted, but the people who are really capable actually exploiting the capability of AI to expand their work, so they don't have to do all these mundane stuff, like setting parameters on your experiment, on your simulations. The AI will do it for you. So ultimately, creating this AI scientists will be your fantastically capable scientist AI assistant to improve your science beyond what it is today. And with that, we believe that the science of AI and AI for science, science of AI is to just study AI as a discipline versus AI for science. So AI for science, AI of science, and especially in computer science, has focused on solving traditional AI problems like image recognition, natural language understanding, and so forth. That's been a 50, 60-year-old problem since the days of like Marvin Minsky and Alan Turing and all that. But AI for science, again, is to solve the most difficult problems using AI. Other problems, rather than image or text. So since AI has been studied for 50, 60 years, and since the proliferation of the internet, there are tons of these data now, right? And they are scavenged, and you have these common data sets. That's how the AI has progressed. But, so traditional data sets are abundant. So this means that the research will focus mostly on training. My model is better than yours. And data is already available as there are corpuses or image sets. That's how ImageNet advanced. Whereas in science, just like HPC, we are focusing on new scientific data, which has never been the target of AI. And the credit will go to scientific discoveries at the end, at the very end. It's not on creating the best model, but it's about the discovery, just like HPC. If you create a program, you get credit, right? Of course, that's very important. In HPC, you create these packages and software. That's important. But if you make a scientific discovery using this package, of course, you get greater credit, and that's the objective. It's the same thing with AI. So due to this, the machine architecture will focus on inference in the science of AI, rather than just training. And trustworthy AI is, of course, important for standard AI, so there are no fraudulent things, or the world will not blow up. But it's a little bit different. The precision and the trustworthiness is a little different, because in science, precision is really, really stringent. But at the same time, because there are ground truth, we can create a loop where it's much easier to come to a tuned AI because of this property. So we're working scaling AI to 100,000 nodes in Fugaku. So Ryo Kota is heading this whole bunch of team of people, including people at Livermore, and with a significant collaboration from Fujitsu, RIKEN and others, to create a training capability. And his team has succeeded in creating a model, which is probably the most performant model, Japanese language model, using both Fugaku and ABCI. But this capability is not so much just to create a new language model, but will give us the ability to do further additional training, as well as multimodal training on these very large machines. In fact, Rio says his team is probably one of the few in the world that's achieved training on heterogeneous, on any arbitrary architecture, instead of focusing on, let's say, one GPU, one type of GPU. And like I said already, things like surrogates are becoming quite normal. So we have people. We have a team at the University of Tokyo, headed by Professor Ichimura, that's created a combined surrogate, but also simulation to improve the earthquake simulation by a factor of 1,000 over the K computer, or about a factor of 25, compared to the non-AI version running on Fugaku. And this successfully, essentially achieves 10 exascale performance that allows he and his team to shake the ground and, with reality, create a true digital twin at unprecedented scale. We also have a case where this is work by a combined team, including Tokyo University and also Fujitsu and so forth, the University of Tokyo, to create a tsunami surrogate, which allows for much faster real-time tsunami prediction. Because even on Fugaku, simulating a tsunami in real time from the time it happens until it reaches the shoreline is just, there's no time. Even if you stop everything, drop everything, do the simulation, it'll take about 15, 20 minutes. And by that time, the tsunami's there, and people can't escape. But with the use of surrogates, they can do this in seconds on a much smaller machine. And then, in fact, they can distribute these results, just like the weather simulation, onto people's smartphone. This time, the smartphone is not saying, oh, it's going to get hot. It's going to say, tsunami's coming, run this way. This will be your closest safest haven on a personalized basis. So they're building a system like that. And we know we've got lots of stuff. We just had one very recently. It can be used for industrial design. So Makoto Tsufuka's team is designing a generative AI coupled with simulations to optimize vehicle design, so that the vehicle will not only be aerodynamically efficient, provably aerodynamically efficient, but also be well designed, will look aesthetic, because it's important for the car to be aesthetic, not just be efficient. The group led by Takahito Nakajima, they're combining, again, their scalable first principle simulations with AI generation, and also with lab experiments to create new plastic, heat-resistant plastic materials which is very hard, which we try to make it out of these biomass. But heat-resistant biomass plastic is really, really hard, but they're challenging that problem. Also, they're trying to create this new type of photovoltaic cells that are the perovskite photovoltaic cells, which are not toxic, but not containing lead, which may, again, revolutionize our energy industry. So, again, these are combinations of ultra-scalable simulations to do the fine details, but also to combine with the generative capabilities of AI to generate candidates rapidly, and then take it to lab experiment. So in fact, the whole cycle, so what we're trying to do with AI for science is to create a whole cycle. We have the foundational models, and of course we have new data sets. So these may be like general foundational models, but we'll do additional training to create customized models per domain. And then we'll do but these models initially will be useless because they'll be so inaccurate. So we need to fine-tune them, and we need to automate the fine-tuning process. So then we'll have this reinforcement learning, or there are some new methods these days, to do the ground truth to the reality of fine-tuning, in an automated fashion, and continuously improve the model, the predictive ability of the model. And then of course, we can get the real-time data acquisition because science is about that. So to establish this continuous loop of data acquisition, model addition, model improvement, model reinforcement, fine-tuning, to continue to establish this loop is the most important factor in AI for science using supercomputers. This will be the generic platform, and of course, there will be different domains. Will be a variant of this. So we're trying to create a white paper. I think the first draft is almost ready, just like we created a white paper when we launched Fugaku initially. We're updating that white paper for applications, but we're adding a new section which will hopefully become independent, thick volume of AI for science. And we've got more than 60 volunteers. Some of you are in this audience. And we're ready for our first version to really say, what are the real scientists doing in terms of AI for science? Not toy apps, not de-sprinkling, not AI sprinkles, the real AI for science. And also need to enhance the capabilities. We are building, we will be facilitating an additional facility here to enhance our AI. Maybe not as powerful as like Aura or some of the DOE machines, but at least good enough. And since we have Fugaku, that's good. So this will be commissioned in 2025. Oh, sorry. Oops. But we'll do this something similar for quantum. So we already have a quantum center, but they're focused on designing and building technologies and a real quantum computer for themselves, and that's very important. We work with them quite a bit. But our job is to facilitate the platform, because what's really lacking in quantum, again, for doing science, science by quantum HPC, and not science of, which RQC is doing, and the lack thereof, the science by, is making hesitant the progress of quantum, because that's what Rick Stevens says. The current status, they lack error correction, etc. We need a lot more qubits, and of course we need better algorithms. And this is resonated by a recent paper by Thorsten Hoffler, my good friend and colleague, and a paper he published with Matthias Streuer at ETH, is that for practical quantum supremacy, you need to achieve exponential speedup. So something like Grover's algorithm, which can only achieve quadratic, will not be very useful. I mean, it's still useful to some extent, but not really useful because it can be quickly caught up by conventional computing. So we really need to investigate these algorithms that have exponential speedup, but they're very, very hard and very few indeed. So we really need the community, the quantum community, to not say, well, they're these toy algorithms, but to really focus on, how do we achieve exponential speedup on for real sciences? In fact, that's how we see the future. So majority of computing, majority of computing which have lower order, non-exponential speedup possible as such, will be done on conventional computers because it's useless to do it on quantum. What quantum is good for will be the regime where exponential speedup is required and thus is intractable in conventional computing. So it's really important to develop algorithms and applications in that space. And then the combination of both will allow optimizations of both, because as much as quantum computers focus on exponential speedup for things like material science apps, then we won't need, let's say, lots of 64-bit LUs, because these will be covered by quantum. Or the classical component can be optimized for the future. And that's why we are embarked on this Quantum-HPC hybrid platform, where we will be facilitating at least 2 quantum, maybe 3 initially. We'll have IBM Q, Heron machine. We'll have a Continuum machine, ion trap machine. And of course, we'll also have Fugaku, and we'll also have another GPU machine running simulators for development. On the classical side, we'll have a Fugaku and of course a GPU system, but the point is not so much just the hardware. We'll try to facilitate, just like the success of HPC was facilitated by the fact that there were supercomputers from very early on for application communities and algorithm communities to use. We'll try to facilitate that by having a common platform that will work across all the machines, be it real or quantum. And this will be likely be one of the largest quantum platform. So we're in very tight collaboration with IBM with this. So we will get their Heron initial 133 qubit processor in-house. And we'll tightly couple that to Fugaku. It'll be downstairs. It'll be the first time IBM will be putting something out of their premise. And of course, if things work out, then we will try to work with them as they have a roadmap for more qubits, but also error mitigation, error correction, and tremendous number of gates, increased number of gates to 100,000, 1,000 qubits, 100,000 in 2023. So, but this will only be usable if we manage to find algorithms that exhibit exponential speed up quantum supremacy in hybrid mode with HPC and present scientific utility. Okay. So that's why IBM is very much interested in working with us. In fact, they're forming a team in Japan to work with us directly. Okay. Finally, I got about a minute left. I'm a little over. Spare me a few minutes. There will be details that will be presented by Kondo-san, who's sitting there. He's a leader of our FugakuNEXT feasibility study. And we have, unlike the previous one, we have a whole bunch of US companies involved. Along with the Japanese companies, we're also talking to additional companies. And also there's significant collaboration with, especially with external, not only externally within Japan, but also globally, especially DOE. And of course, the reason is that we realize, again, it's not about building one ginormous machine that are customized, cannot run any other code. Okay? It's about the science. It's about dissemination. Our results need to be disseminated. If our results get into every, let's say, if some of our technological development gets into every platform, as I say, for example, working on certain things, elements like networks and memory. If this technology gets into every GPU in the world, that's a much bigger success than building one machine. Right? And that's what we're aiming for, not to build one big machine. So, of course, we need our applications. So the application group has really came up with all these things and details we spoken to by Kondo-san. And there is a, what do the next generation application look like for simulation and AI? But all of these, we realize that most of the applications are memory bandwidth bound, and to some extent network bound. So increasing, as we have been preaching for the past 10 years, increasing flops is inconsequential to application speed up for the most part. Even AI, training may be compute bound, but inference is memory bound for the most part. So given this analysis, where should we focus on? Should we focus on a new CPU? No. Shall we focus on a customized FPGA? No. What we should focus is data movement. Because ultimately, ultimately, the performance limiter will be energy of data movement. And without going into details, Kondo-san will explain later. But just to say that our goal, our ultimate goal, may be next Fugaku, maybe one after that. In order to get more than order of magnitude performance increase, given that many applications are memory bound, the energy budget we have to move the data from memory to the processor is only 0.2 picojoules per bit. So what's 0.2 picojoules per bit? Okay? The 0.2 picojoule is when you have a chip, the latest, greatest chiplet interface. Right? Just connecting two chips together, chiplets together, getting the latest spec, getting a chip, getting a data bit from one edge, one chiplet to the other. That's more than 0.2 picojoules per bit. So just moving the data on two adjacent chips is 0.2. So there's just no way. It doesn't really matter if you increase to go to zettascale. It really doesn't matter if you have all the LUs in the world. Doesn't really, what matters is you have to minimize the energy for data movement. And that takes hardware, takes packaging, it takes architectures, microarchitectures, it takes software, it takes algorithms to localize data movement, it takes everything. And but that's where the innovation will come. Okay, so working on that. And of course, we have to care a little bit about dense linear algebra, but also working on that too. But I'll skip since data is running. I'm running out of time. Okay, so that's where we'll be. We are. That's where we are. That's where we're going. So we're transcending from a center that develops this flagship machine, a flagship machine, and being a caretaker, to a center that will facilitate, and will do research on, facilitate, and work with the application community, multiple machines. We may keep the old Fugaku alive if it's good enough when we commission a new one. The last time would have been, the biggest mistake we made was to decommission K, then commission Fugaku. There was a 2-year gap. But now we'll have multiple machines. We'll have Fugaku. We will have the AI machine. We'll have the Quantum-HPC hybrid. We'll have FugakuNEXT. There's a high chance that all these machines will operate in parallel and then decommission in a staggered fashion, because it's all about facilitating the infrastructure. And we'll have the infrastructure, software infrastructure, domain infrastructure on top, consisting of components, simulation components, application components, and their workflow. And we'll get the real problems done. We're transcending into that mode. Instead of, again, be a one-trick pony of running one gigantic exascale machine. So with that, I'd like to end my talk. Thanks.